Hi everyone, I'm Henrik. I'm at the University of California, San Francisco, which is a medical school. I've been using R since fall 2000. Everything I'm presenting and everything I'm building comes out from research projects. I work a lot of genomics data. Sometimes it's small data, sometimes it's big, sometimes it's huge. My collaborators are people with laptops. Some people have huge compute clusters. Others are like that poor technician in the end of the hallway in a lab. And everything, all the statistical methods and everything, algorithms we implement, and all of these people should use it. And this is something that got distilled out of this. And I decided to do this back in 2012. And then 2015 I came out with it. So I'm going to talk about futures. It can be used for parallelization and distributed computing. It can be used for other things too, but we will focus on parallelization. So why do we parallelize programming? Typically we want to speed things up. That means instead of taking 5 minutes, we want things to take 1 minute. Other people have it takes 2 weeks and they want to get it down to less than a week. Sometimes we also parallelize because we can't fit everything in memory. So we could split it up in time and run smaller chunks. But if you have multiple computers, you can split it up across computers. So that's another reason why we parallelize. And then we have, for instance, user interfaces. There is Shiny is one example where people want to have the user interface should still work, but you have things running in the background. And what I'm presenting today can be used with Shiny as well. So let's start with concurrency here in R. It's often used in the context of parallelization, but it doesn't have to mean parallelization. So imagine this list of 3 elements, and each of the elements has a set of numbers. And we want to calculate the sum of these elements. And we can store it in another list we call Y. So we could do it this way. We could do it manually, element by element. This becomes tedious. It's error prone. When we get more elements, we can do a lot of cut and paste. So we typically do something like this. We turn to a for loop, and we iterate over the elements available in the list. And then we all know about the list apply, or lapply, that we say, operate the sum function over this list and store it in Y. So key to all these approaches is it doesn't really matter which order the calculations are done, as long as we have input and output, and they all give the same results. So here it comes in how we can, when we have these concurrent approaches, we can start thinking about parallelization. So now imagine for the sake of the example that this sum function is very slow. So if I call it slow sum here. So it takes 3 minutes to do this, 1 minute for each of these elements. Very slow. In R, since many years now, we can do, if you're on Unix and Mac, you can do mcapply. So you can switch your lapply and use mcapply and say, I want to run it in 3 cores. So it's going to be 3 workers running on this, and it's going to take a third of the time, 1 minute. If you're on Windows, you can't use this. But you have other options. You can set up a set of background R sessions running. You export the objects that those session needs, and then you call the parapply. And you get parallelization there as well. And then as a developer, you might think, okay, I want to support both. So then your code might be say, if on Windows, do this. If on otherwise, do mcapply. And then you might keep growing this code and say, if I want to have multiple computers, you have another if statement. And that simple code statement, the 2 lines at top, all of a sudden becomes like giant, big mass, very hard to maintain. So that's where, so you have things of which API should I pick, or which one should I support? Who are my users? Who are my future users? I don't know them, but they might come. And maybe you're too busy to be bothered to support Windows, or you try to support it by implementing, but you don't test it. And users might have other wishes than you as a developer. So it's a lot of things and decisions, and it's annoying when you develop code and implement methods. So that's where futures comes in. So all these parallelization mechanisms we have available, they have something in common. And the future frameworks try to encapsulate that, so you don't have to worry about that as a developer or a user. So to be clear here, I implemented this in a package. And the package is, the motto is like you can write once and run anywhere. 100% cross-platform. Very simple API, basically just 3 functions needed. Super easy to install. It only depends on the parallel package that comes with R, plus a globals package. And it's lightweight. Very well tested, used for many years in big. I've been processing petabytes of data with this. Other key strengths, I think, is that automatically identifying and exporting global variables. If you know parallelization, that becomes tedious sometimes. And you can also do it manually if you want to. It also relays output you print, or messages and warnings that are created. And those are relayed, so if you run it on a remote machine, it will come back to your local computer. And if someone else creates other parallel backends in the future, that it will just work. So more formally, a future is, the concept of futures is a programming concept, and it was invented in the mid-70s. And a future is an abstraction for a value that will be available later at some point. The value is a result of an evaluated expression. And the state of the future is either unresolved or resolved. So if we make a little bit of code example here, we think about an R assignment. In R, we have a left-hand side and a right-hand side. On the right-hand side, we have an expression. It can be 1 + 2. It can be a very complex expression. And when R sees that, it evaluates it and gets the value, the result of that expression, and assigns it to the variable B here on the left-hand side. And if you think about it, there are 2 steps here. So the future API basically provides you access to those 2 steps. It's going to be clear soon, I hope. But so you can create a future with the expression, and you have a handle to that future. And later, when you're interested in the value, you can say, hey, give me the value, and then you get the value. And this is a very powerful thing. So back to our slow sum. So now let's say we sum 1 to 100. That will take 2 minutes. Sum is an operation that can be parallelized. It has this feature, you can sum the first 50 values, and you can sum the second half of the 50 values, and then you can add them up, and you get the same value. We didn't gain anything here in speed, because it still takes 2 minutes to run this. But the thing here is now we can start parallelizing. So if we turn to the future framework, we load the package, we say we want to parallelize on the local computer, and then we create a future for the first sum, and that will return immediately. And it will start running in the background. And we can do second future, start running in the background. And we still have the prompt here available, and we can do whatever we want, calculate the mean or whatever. And now let's say 50 seconds later, we say, give us the value. We know it takes 1 minute for those to run roughly, so we have to wait for 1 minute here, or 10 more seconds to get, and after 10 seconds, we get the result. And by this time, the second future is probably already done, so that's non-blocking, it just gets there, and we get the value. And here we could now compute the 2 blocks in total wall time of 1 minute. And here is the design here is that the user decides how to parallelize it. The user can say, I want to run this sequentially, I want to run it in parallel on my local computer. I want to run it on 3 computers in the office, or 1 computer in the office, 1 in the cloud, 1 at the university, or on a compute cluster with a job scheduler. There are many, many different ways for the user to run the same code in parallel. And as a developer, you never change the code. So I mentioned the function future and the value. There's one more called resolved. You can ask, you can check in on the future, say, are you done or not? And it will say true and false. But with these 3 constructs, we can build much more powerful parallelization APIs higher up. So as an example, if you want to go ahead and create your own lapply in parallel, this is what will look like the first approach, and it will work. So you basically take, this is, if you want to iterate the function fun over the elements in X, you would just do that inside a future. So you get like a lot of futures to handle, and then after that you say, give me the values. And the future framework will just parallelize this if the user decided to do so. So this will return in 1 minute. So then you can add a little bit more things to it, but chunking and things like this, but that's the gist of this. So these 3 functions are very useful. So I went ahead and did the future apply, which implements all of the base R, lapply, bapply, etc. And they work the same. You can just prepend future underscore in your code, and it works out of the box. And then the user can decide how to parallelize. There are other frameworks that do the similar thing. So Davis, he did the same internal thing with the per framework and use futures and values in there. And then if you like, you can use the for each framework too, to use futures. Okay, so I'm going to go to the second one. And I never talked about this, but when I presented this talk, I think I presented futures 3 years ago, first time. And I'm sure like within a day, can we put progress bars? And people keep asking about progress bars. And this is how I feel about it, because it's very complicated. It's easy when you do it on your local machine sequentially. So why is it complicated? Or, I mean, number one is, and I'm not claiming I solved this, but I found a step towards this. You present your progress bar locally, but your workers are running remotely. So of course, that information needs to get to the main process, so that's a main one. But then also we want all your code you write with futures should work the same. So it has to work with all backends. So progress updates has a nice feature. If you don't get them, it's not the end of the world, but so that makes certain things easier, but making things work the same. So you shouldn't have to code differently depending if it's on a local machine or a remote machine. And also, there is the progress bars. I'm not a big fan of the bars word. Different packages choose to display progress differently. I see you pointing at 2 minutes. When did we start? 25? Yeah, that's okay. Good. I agree. Sorry. Yeah, and how progress is presented is decided by the developer and when the package is submitted. The user has very little control of this, and more importantly, not everyone can use progress bars. So you can imagine screen readers. Worst case, this one will be like equal sign, space, 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 and then your updates, equal sign. So that's not a good thing. So I decided skip progress bars and call it progress updates. So you can split it up. So the developer decides to update what to update, just signal progress updates. create a progressor for 10 steps, and you say, you call the P function here, and you do that in your iteration. And the end user just say, I want to listen to progress bars or progress updates or not. So that's separation. So if the code will look like this, you have your loop over something, and as a developer, you just add, I want to use signal progress here, and I can send a message with it. And the user, if you don't listen, nothing will happen. But you can choose to say, I want to have progress updates coming, and you get a progress bar. And this is handling with R's condition system. And this is a prototype and proof of concept. And users can choose different backends, built-in text progress bars. You can use the progress package. More fancy, you can use beeper if you want sounds. You can combine them. And if you want to have progress bar and a ping when it's done, you can do that. Okay, I'm going to use 2 more minutes. Sorry. You can use RStudio's API, Shiny API. You can send updates with a push bullet or email or voice calls or whatever. And this just works also now with the future framework, because the future framework doesn't have to know about this. It just works. We've got to that point. So anyone who asked about progress bars, we made a major step forward. And I talked to Gabor on Wednesday, and I had a 2-hour talk to him. There he is. And super exciting news. He's been, of course, like everything else, thinking ahead of this. So I haven't tried it, but I think his progress package, he has work in progress, not the one you can down from CRAN, will work with this out of the box, meaning I don't have to implement it. So I'm super happy with this. So I want to say thank you, and room for one question maybe.
Thank you, Henrik.
Hi, I just want to say thank you for the package. I might be Future's biggest fan in the world. So my question was, often I have to write basically complicated functions, but it's great that Future detects what's in the global space for me and brings it in. But sometimes I feel that there's something that I sort of need to tell Future. Yeah. But what happens then is, if I tell Future to use these things, then it doesn't automatically detect all the other things. So I was hoping that, is there a way to do it so that Future will continue to detect as per normal, but if I go do additional this?
Yeah, you can say, find everything automatically, exclude this, or include this also. So you have full flexibility to control globals. Yeah, if that was the question. Yeah. Look at the help page there. You can do everything I think you want. Yep.
So we have time for one short question.
Thanks a lot. What happens if the user calls a future lapplyo without calling plan first?
And the default is sequential, and that's on purpose. Yeah.
Yeah. Let's thank Henrik again.
Thank you.